Okay, for the last several videos, we were looking at first-order differential equations and how to solve them. And we used a theorem for equations of this type, y prime plus p of x, y equals g of x. And we had a theorem where y is equal, if it's of this form, y is equal to 1 over mu of x times the integration of g of x times mu of x dx plus c on mu of x. And mu of x is given by e to the p of x dx. So that's a general theorem for solving first order linear differential equations. Then we had looked at y prime plus p of x, y equals q of x, y to the n. Now this was called a Bernoulli equation, differential equation, and we could use a Leibniz substitution, which is v equals y to the 1 minus n. And so, by making that substitution, we can convert the Bernoulli equation into a first-order differential equation. So, our second item was converting Bernoulli equations into linear form. And now we're going to take a look at something closely akin to what we've been talking about over the last couple of videos. And in that, we were given y prime equals 4y times 1 minus y. Now, some of you may recognize this form. This is in the form of what they call the logistic equation. The logistic equation is something of this nature, kx times 1 minus x. It's a nonlinear equation. It was one of the first to be studied in chaos theory, and it's used in population studies, among other things. It, for example, if you're given a population of deer in year 1, and you have x naught deer in year 1, then we can predict year 2 by plugging g of x, by plugging x naught into the function k x naught times 1 minus x naught equals x1. So our predicted value for the next year is x1. But then if we want to know for the following year, year 3, we then use x1 as our new starting point. So we got k x1 times 1 minus x1, and that gives us x2. And so for that next year, we have a prediction for year 3. But then if we want a prediction for year 4, then we use x2 as the input again. 1 minus x2 equals x3, and that's our prediction for the next year, and so on. So we have this sort of circular relationship where the output becomes the input. So the output becomes input, and that's called a recurrence relationship. And this has some pretty wild properties when you vary k, the constant, the rate constant. So if you start out with an initial x, let's say you start out here with x naught, and you plug that into k naught, x naught times 1 minus x naught, and you crunch this out, where the output becomes the input, and then the output becomes the input again and again. So it goes back and forth in this recurrence relationship. If you plot this for a given k, so for a k, so for k equals some value, let's say 1, we'll see initially when we start with x0, x, we'll see that initially that the function begins to rise and then stabilize at a number. So it goes to a certain number. So after crunching it some n iterations, big number, let's say 10,000 cycles, it will flatten out to a single number, the output. Now you vary k again, and it'll do the same thing. It'll initially have a few points and then flatten out to another value. And then k3. And again, it does this and then flattens out to another value. Well, if you continue to vary k, so if you continue to vary k, let's get this. If you continue to vary k, you begin to get what they call a bifurcation diagram. So if you increase k, you begin to get a diagram like this, and at a certain k, so let's say this is k1, k2, k3, it will bifurcate. In other words, the output then is not a single number, but becomes, it oscillates between two numbers. It stabilizes after large number and large iterations. It'll bifurcate between two values, x1, x2. And then, as you continue to increase k, it will bifurcate again. I'm not the best artist, please forgive me. And again, and actually the distance along k actually diminishes. So you reach, let's say, this k n. The k's that cause the bifurcations become closer and closer, and you end up with all these bifurcations, and then you get k threshold. There's a threshold value of k where the value then becomes chaotic, and you end up with some kind of output where you got thousands, millions of little points, but there's no pattern to them, except every so often there will be a small window that looks like a bifurcation diagram, and then back off into chaos, and then there will be vacant areas, and there will be areas where there's of high density. And so you can do this yourself. It's pretty crazy for g of x equals k x times 1 minus x. You can do it in Excel spreadsheet. In fact, I got an example. It's a crude example, but it's an example in Excel. And you'll see what I mean about the bifurcation diagram. And I can also show you some bifurcation diagrams on the internet. But anyway, that's those are some of the characteristics and the properties of this logistics equation. But there are some other aspects of this more in line with our area of discussion that we've been considering over the last several videos, in differential equations and their solutions. So if we're given this equation, differential equation, times 1 minus y, we have, if we expand this out, y prime equals 4y minus 4y squared, and then y prime minus 4y equals minus 4y squared. And now we have a Bernoulli equation, and we can use Leibniz substitution, So minus 1, because n is 2. 1 minus 2 is minus 1. So v is negative 1 equals y. And then we differentiate minus v, the minus 2, v prime equals y prime. And we plug that back into our equation. So we got minus v to the minus 2, v prime, minus 4y, so that's v to the minus 1, equals minus 4 v to the minus 2. And that's our new equation. And if we multiply through by minus v squared, we can make this a solvable equation. So we have v prime plus, plus 4v equals plus 4, and yes, that goes to 0. V minus 2 plus 2 is v to the 0, and then we use our solution here for v equals v of x equals 1 over mu. Mu of x is equal to e to the 4 dx, and that's equal to e to the 4x. So this is equal to e to the minus 4x raised, or times 4 e to the 4x dx plus c e to the minus 4x. Oh yeah, and we were given an initial condition, y of 0. Let's see, what was it? 1. Let me check the book. I'll be with you 1 second. Okay. Yeah. What's that here? Yeah. Oh yeah, that's the equation. So we were given no. Interesting. No, we were not given an initial condition. So we will then continue. So we have e to the minus 4x, and we have, if we do a u substitution, u equals 4x du, 4 equals dx. So we have 4 on 4 e to the 4x plus c e to the minus 4x, and we have 1 plus c e to the minus 4x. But then this is only for v of x. Remember, y of x was 1 over v of x, so we say y of x is equal to 1 plus c e to the minus 4x to the negative 1. And that's our solution. But what if we couldn't solve this? What if we weren't able to solve it? What could we do? Is there anything we can do? Well, and there are a lot of integrals that we can't solve. There more integrals that we can't solve than are able to solve, actually. And but what's interesting is we can extract information about the original function by using the knowledge inherent within the function itself. And what we do is for any given x, so let's say we have an xy coordinate system, and we have y here, and where's this function defined? Well, it y prime becomes negative. Y becomes less than 0 for y's greater than 1. Y prime, I mean. For y between 1 and 0, we have y prime is greater than 0. But then again, below 0, y less than 0, we have y prime less than 0. So we're given some information. So in here, between this range, so y, that's y, and this is x. This is 1 and 0. All of our slopes, because y prime is the slope or tangent of the curve for a given x. So we can use that information to help us out. Now at y equals 1, y prime equals 0 at y equals 1. And y prime equals 0 at y equals 0. So in other words, whatever tangent we have, it's flat. So what we have then at 1/2, we have y prime equals 1 at y equals 1/2. So at any value x at 1/2, y equals 1/2, our slope is going to be 1. But then it begins to flatten out as we approach 1. I'm not the best artist, so please forgive me. And again, it does. And remember, it's always positive in that region between 0 and 1, but it flattens out towards 0. So we get this S shape. And if we plot this along x, we could see that our curve is going to look a little bit like an S, like that, between 1 and 0. And so even, let's say we're not able to integrate this is the interesting thing. Even if we're not able to integrate this function, just knowing the tangent at given points of the curve yields information about the curve. And if we create what we call a directional field, this is a directional field of tangent points, we are able to get information about the function, namely that takes that form, and the inflection point is at 1/2 y equals 1, y equals 1/2, y equals 0. And so that is an interesting, very interesting result. Created a field, what they call a directional field, first off for y equals x squared. So this is the data for that, and this is, let's see if I can, yes, here's the directional field for the function. Now, I plotted the function y equals x squared. You can see it here. I didn't match it exactly, but you can see that the derivatives create a field of slopes, tangent slopes, that yield very definite information about the function itself. So even though, let's say, we weren't able to solve the particular integral that yielded the parabola y equals x squared, the directional field, the slopes, give us plenty of information about the the function that we're dealing with, even if we weren't able to integrate it. I think that's pretty cool. And I plotted a parabola just to show you how close the directional field will give you information regarding the particular parabola. I actually raised this parabola. It probably should be a little lower. I think the curves here are probably more representative of, I displaced the parabola y equals x squared up the y-axis a little bit. So anyway, you get that point, but that's just for y equals x squared. And I recommend that you try it yourself. It's pretty fascinating to see how this works. Now, the function that we had been talking about, the logistic function, this is a directional field that I plotted from the function itself. What I did was I solved for the function, and then I took the derivative of the explicit solution and created a field of slopes from this y equals 1 minus c e to the minus 4x, all raised to the negative 1, for given x's along the x-axis. And you can see here how the slopes change in the vicinity between x equals minus 1 and x equals 1. And the maximum slope is at x equals 0, where the slope is 1. So it just shows you how that the tangent functions, or the derivatives of the explicit function, yield these tangents, this tangent field. But in this case, I did solve explicitly. You don't necessarily have that ability to solve explicitly, so you use y prime equals 4y times 1 minus y, and you can create a field from from that data, and this is the field that comes out of that. Now, for a given y above 1 and below 0, you can see that the slopes are negative. For instance, the curve diverges away from the 0 line. This is y equals 0. You can see that at y equals 0.5, that the slope, no matter where you are on the x-axis, the slope is always going to be the 1, and it's always going to be the maximum at this point, no matter where you are on the x-axis. And then as you increase further along the y-axis, the slopes decrease and flatten out to y equals 1, where the slope is 0. And it gives you this S shape. I did it by hand on the Adobe Sketch, but that wasn't as nice and neat as what comes out of Excel. If you use Excel, this is pretty cool stuff. You can do it yourself. And again, notice up here above y equals 1 that the slope of the curve is strongly negative, but then flattens out to 0 at y equals 1. So you have a strong curve that would go this way. It's very steep, almost vertical, and then it curves very sharply, flattens out. But remember, our function is not, this is not the domain of our function. Our function will not exist outside of y equals 0 and y equals 1. Or it will, but not for x. When we look at x, the function will not plot values outside of y equals 0 to 1. That's our y range of domain, our y domain for the explicit function itself. And so we can get very important information just from the tangent points themselves, and then plotting a field of data. I've got a little more. I had talked about the other properties of the logistics equation from a chaos perspective, and I created this little model here where it calculates, I think, something like 180 iterations. And you can see what I'm saying here. So for y equals, or k equals 1, for x naught equals 0.1, you can see it's not exactly flat, but it's flattening out. And if I went, let's say, 10,000 iterations, it would flatten out to a certain number, a given number, and it wouldn't deviate from that point. If I raise this to k equals 2, you can see, again, it takes fewer iterations for it to stabilize out. I think, again, I went 170 iterations, and this is a pain in the neck. I did 170 iterations, and this thing will flatten out at 0.5. Now, if I go to k is 2.5, you can see that x will flatten out again. It's around 0.6. If I go to 2.7, then it goes to 0.6, 3, something like that. About 0.63. And when you start getting into the 3s, you could see it's beginning to split. You can see the line has gotten very thick here. It's bifurcating. It's actually come to a point where it's actually bifurcating. So for k equals 3.1, we have a very definite bifurcation between two values. And the two values are about 0.56 and 0.77, something like that. It's close to that. You can see. So let's take a look. This was 3.1. Yes, it's bifurcating between 0.56 and 0.77. Now, if I bring that to 3.5, you can see I created a table here. This thing here is a table of the values of x for a given value of k. And you can see for k equals 3.5, and I didn't vary the initial x. The x naught is still 0.01, but the function levels out at 4 different points. We've got a second bifurcation. So the way the bifurcations work is geometric. They go by 2 to the n, and so every time we have a bifurcation, we have another doubling of the number of the values of x that it stabilizes to. So here we have a bifurcation of 4 values at 3.5. Let's see if we can, at 3.56, as you can see, it doesn't take much varying at this point now. Well, at 3.56, we end up with, we have 1, 2, 3, 4, 5, 6, 7, and 8. These bifurcations are small to see. You can't really see the difference very much, the way we're plotting on the axis. I made a larger plot. Whoops, that's the bifurcation diagram. Here's that little plot that we were looking at. You couldn't see the oscillation between these two as easily as you do here because of the scaling difference. But you can readily see that we got one value up here, another value there, a value here, a value there, again here, there. So we got 1, 2, 3, 4, 5, 6, 7, 8 separate values. And as we increase, we go to 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, and then we reach a k value. Here we go. Where's our? Let's see. Okay, we reach a k value, 3.6, where it begins to go into chaotic realm. You can see here it's hard that the values are unpredictable. You can't really say what value is going to come out of the function. There's no pattern. There's no stabilizing to certain values. Although there's an area of absence, this is a vacant area where there are no points. But within these areas where the points do exist, the output does exist, there's no pattern that you can see. And as we progress into the chaotic zone, you could see that the output is unpredictable. Although it's bounded here. This is our attractor, is the boundary. Values don't exist outside this boundary. They all exist within this area. So these are what they call strange attractors. There isn't a single point at which the function converges anymore, but there's a range of values within which the function remains, and that is our strange attractor. So all of these terms come out of chaos theory. And that's not really the main point of what we're discussing in differential equations, but it's interesting nonetheless, since we were given the logistic equation as an example. And again, now here's our k value, and these are our x's here, and then I plot these x's, and I just went to 8 bifurcations. 1, 2, 3, 4, 5, 6, 7, 8 bifurcations, and I didn't even smooth the curve. I just and you can see how they branch out, and as we vary k, actually I put this on a log scale, so it was a little easier to see. This isn't really as sharply bent. That's as a result of the fact that I plotted it on a log scale so that it is easier to see the form. This x-axis or k-axis, if we vary k just a little bit more, these branch out very rapidly to 32, 64, and so on branches, bifurcations, and then boom, you hit the threshold value of k, and we enter a chaotic realm. And I just wanted to show you this because that's kind of a crude bifurcation diagram. If we look at Logistic Equation wiki, we can logistic function. Okay, that's you can see our S curve, our logistic function, but where's our bifurcations? Okay, it's not in this. This is just talking about the function itself, the logistic equation, bifurcation, logistic map. Okay, so here we go. This is the evolution according to iterations of the bifurcation map. And you can see now this is not plotted on a log scale like I did. So these are your k values, your constant as you vary the constant, and the function itself, the output of the function, the more iterations that you go, the values become more and more discrete. So you get this nice bifurcation diagram, and you can see the splits. Here we go. This is another bifurcation diagram. Now this is what I was talking about. Here again, they call K R here. These are the values that the logistic function takes. This is our initial bifurcation, somewhere in the vicinity of 3. Our second bifurcation right here, around 3.4 something, 3.45. Our third bifurcation, and you can see how we don't have to move much along here, and the bifurcations occur more rapidly. And then we enter in to the chaos zone right here. And you can see that there's a vacant area in there. But then as you proceed with k, that area begins to fill in as you move along the k-axis. And you can see that there are areas free of data, and you can see little zones. They're not evident here, but like this, it's very difficult. But where I have the magnifying glass, it looks like this over here. It's like areas of what they call pseudo stability. So that's where, even in the chaotic realm, the function begins to stabilize. And I think this is what they do here. They magnify that. Here you go. They're magnifying. There's this. If you take a very close look, I think I can. There we go. Look at this. This looks like our bifurcation map upside down. So it looks like back here, further back, but inverted. So you can see it inverts itself. And this is an area of pseudo stability. And again, you can see here, again, that pseudo bifurcation. So there's fascinating stuff about this nonlinear dynamics. But again, that's not really the main point of our discussion. We're looking at functions, main characteristics of nonlinear type functions and how we can get information from them. Now I'll pull down another. Oops, I'm gonna save that, and I will open up another. I think it's interesting. Another spreadsheet that I created. All right. I call it ODE2. Let's see if I can search ODE. Is this my... Nope. Sorry. This... I gotta get my right drive. It'll open up in 1 second. Let's search for ODE 2. ODE field 2. I'm gonna have to download this because I don't like working in sheets. Okay, so let's download. Download as Microsoft Excel. And it's on desktop. So we're going to save it and open. Okay. I really don't like sheets. I'm not wild about Google. Now, this is the same spreadsheet with a few more functions added to it. You can see that. Now, here is y prime. Y prime is equal to x squared plus y squared. So in this case, let's see if I wrote it down anywhere. Well, I did in the tab. Y prime equals x squared plus y squared. So this function has got let's see if I can. This is y prime equals x squared plus y squared, and I'll try and magnify that a little bit. No, that doesn't work. I just have to enlarge the font. Come on. Come on, come on. There we go. Y prime equals x squared plus y squared. And what I did was I created this Excel sheet. Here's our x values. Whoops. Let's undo that. What I meant to do was this. That's our x-axis. And these are our field of lines, little line segments that give us tangents at points on the curve. So, for example, the little line that I created is the tangent point at x equals negative 2.9, and so you can see that the slope is going to be the same for this x value, even though I have different y values. So I get line segments, and then I plotted that on an xy coordinate system to give me, the this right here. Okay, so let's see if we can increase this in size a little. You can see here now the tangents yield this you can see the field yields a sort of an S, a sideways S, like the yellow. Now the yellow is one of the extreme sets. I plotted between two different y values, and the yellow is the one that passes I think maybe they all pass through 0. But if you were able to take the integral of the function and plot it, this is what you get. So you can see how the field gives you, this is y equals 1/3 x cubed. And that's what this plot is here. And you can see that our directional field yields that form of curve, and you can see that here, where this would be the tangent points along that curve. And these are, various curves. If we had different constants along, these would be the tangents of those curves for various values of the constant, because we didn't solve for the constant. And if we look at the function, let's take a look at how we arrived at the function itself. And we'll exit out of Excel here, and we'll go back to our drawing board. Okay, now when we were looking at our Excel spreadsheet, we saw the directional field for y prime equals x squared plus y squared. And we saw how that yielded a curve that was sort of, I'm a terrible drawer, sort of like that. Let's start again. When we looked at our Excel spreadsheets, one of the directional fields that we created was for y prime equals x squared plus y squared. Now, if we remember what the directional field looked like, it on the xy axis, I'm really bad at this, so please forgive me for my poor artistic quality. This is our y-axis and our x-axis, and we had a function sort of like this. It's y equals x to the third on 3, and that was the general shape. It's hard to draw, especially for me, to draw clearly on the on this board. It's not not the easiest. I'm not the artist in the family, but if we now again that directional field technique helps us understand what characteristics exist within the function. If we have dy dx equals x squared plus y squared, and we have y of x equals x squared dx, you can see what we have here is a cubic function. Plus c. And you can see if we take our dy dx, we have x squared plus y squared. And it yields this cubic. And that cubic plots, again, a function sort of like this. In that general shape. So our directional field gave us some very good information. So I just wanted to show you that that indeed makes sense, and that this is pretty interesting stuff. Now, there's some other problems that we had that we looked at, that I looked at, and I thought would be good to go over. So let's take a look at some of these. I got the logistic these are the notes here. Directional field. Okay, here's some problems that they gave us to solve. They're listed on the page 30 of the Boyce and DePrima textbook I've been working on or using. And what they want, they say, for each of the following equations, state the region in the xy plane where the existence of a unique solution through any specified point is guaranteed by the fundamental existence and uniqueness theorem. So right here, we were given the function y prime equals x minus y over 2x plus 5y. Well, we can't have the denominator can't equals 0. So 2x plus 5y cannot equal to 0. So the domain of this function, of the region, basically, it says state the region in the xy plane where the existence of a unique solution through any specified point is guaranteed. And so that would be for 2x plus 5 is less than 0, and 2x plus 5y is greater than 0. And this is where we have a solution. It's the region where a unique solution exists. And this is excluded right here. Now, this is problem 1. Problem 2 was y prime equals 1 minus x squared minus y squared to the 1/2 raised to the 1/2. That thing just told me our battery is running low, so I better plug her in. All right, that should work. Let's see. Yep, it's charging. All right, so let's take a quick look at this one. So this is a square root. So, oops, really hate that. This is a square root. So 1 minus x squared minus y squared can't be less than 0. The argument can't be less than 0 inside that square root. So if we do a little algebra, x squared minus y squared is less than -1. So therefore, x squared plus y squared is less than 1. And that is where we're not defined, except in the imaginary realm. But in the real world where we can't. So everything that is outside of this constraint is allowed. The next problem they gave us is 3, where we have y prime is equal to 2xy over 1 plus y squared. Well, we can't have the denominator equal to 0. But in this case, the denominator is never 0. In fact, it's always positive. It's always greater than 0. So the realm in which there is a region in which there is a unique solution is the entire xy plane. So this is defined everywhere. the whole plane. Now, just a couple more problems. Hello.
Hi. Oh, hi.
We got this right here. 1 over 3 times x plus y squared. We can't have x plus y equals 0. So that we can't have. So x plus y less than 0 and greater than 0. That's our region. This is where we're defined. That was problem number 4. Number 5. We've got this one. This is interesting. Y prime equals ln x, y, and 1 minus x squared plus y squared. So we can't have 1 minus x squared plus y squared equal to 0. So we have 1 minus x squared plus y squared less than 0, greater than 0. And we have, or we could do it x squared minus y squared is less than 1 or greater than 1. We could do it that way. And we have to be careful here where x, y equals 0, because ln of 0 is not defined. So we have two conditions. So we can't have x, y equals 0. So x, y is going to be greater than 0. So that's an interesting one because of the natural logarithm. And we got other problems that we can solve. But I got visitors, and so I'm going to put this on hold for now. We're picking up from yesterday, the continuation in this video, where we were given problems A, y prime equals x minus y, 2x plus 5y. B, y prime equals 1 minus x squared minus y squared to the 1/2. C, y prime equals 2x y over 1 plus y squared. D, y prime equals 3 over x plus y squared. E, y prime equals ln x and 1 minus x squared plus y squared. And F, y prime equals x squared plus y squared to the 3/2. Okay, So for the first problem, A, we don't want the denominator to be equal to 0. So 2x plus 5y cannot be equal to 0. That's a that would make the y prime go to infinity, and it's not a it doesn't allow us to find a solution at that point on the xy plane, which is the purpose of the problem, which is state the region in the xy plane where the existence of a unique solution through any specified point is guaranteed by the fundamental existence and uniqueness theorem. So the denominator can't be equal to 0, which means then that 2x plus 5y is either less than 0 or greater than 0. Now, for the next problem, B, we can't have the argument less than 0. We can't have a negative argument with a square root. So 1 minus x squared minus y squared has to be greater than 0. And that's the region in which there's a unique solution in the xy plane. For number C, or letter C, we have 2xy over 1 plus y squared. And again, we look to the denominator, and we know that the denominator cannot equal 0. But in this case, our denominator is 1 plus y squared. And no matter what, that is always greater than 0. Always. It's never 0. So this is defined on the whole xy plane, or everywhere. The next one is a little trickier in that it has an appearance of being a square, but the problem is we have conditions where the denominator could be 0, and we have to stay away from denominators that are 0. So when is it 0? Well, when x, y and x are equal to 0. So x and y have to be greater than 0. And when x is equal to negative y, or negative y equals to negative, or y equals to negative x. Okay, so we have to say x is not equal to negative y, or negative x is not equal to y. And that's the region we're defined in xy plane. Now, the next one is kind of interesting because we have the ln xy in the denominator, in the numerator, and we know that when, let's say, we have a function g of x is equal to e to the x, there is no x no x value that would make g either 0 or less than 0. So there's no, it's undefined. The ln of 0 is undefined. So x cannot be 0, neither can y. So neither one of those can be 0. And the denominator we have to say is not 0. So it's either less than 0 or greater than 0. Those are our two conditions for the function to be defined. Defined solution in the xy plane. And finally, the last one, we can see that that's times x squared plus y squared to the 1/2. And we can't have an argument x squared plus y squared less than 0. So that's not possible. X squared plus y squared is greater than 0 always in the entire plane. So it's defined everywhere. It's like letter C. The same situation as letter C. So with that, we move on to some other problems. All right, so let's look at this again. We are given the problem y equals 1 minus x squared to the 1/2, and show that it is the solution to y equals 2x y to the negative 2. Or plus. That's correct. With y of 0 equals 1. All right, so we see it's a Bernoulli equation. We use v equals y to the minus 1. So v to the minus 1 equals y. So we have minus v to the minus 2, v prime equals y prime. So minus let's take a look. All right, let's look at this again. We are given the problem to verify that y of x equals 1 minus x squared to the 1/2 is the solution to y prime equals 2x y to the second power, with y of 0 equals 1. We use a v substitution because it's a Bernoulli equation. V equals 1 minus n. So this is equal to, that's 2, yep, equals y to the 1 minus 2. So it's that. So we have v to the minus 1. Yeah, this is the, you know what, this is the problem. I'm looking at two different problems.
Is there a map?
We are, this is not the solution there. It is this to the negative 1. That's the correct solution. All right, so verify that this is the solution to this. So we have y, so minus v to the minus squared, v prime equals y prime, and we substitute that into minus 2v prime equals 2x v to the minus 2. All right, so now we have the problem. Multiplying through by minus v squared, we end up with v prime equals minus 2x, and that gives us dv dx equals minus 2 dx plus c, which gives us v of x equals minus x squared plus c. But we realize that v of x, 1 over v equals y, so y of x is equal to c minus x squared to the negative 1. And we have the initial conditions, so y of 0 equals 1, which is equal to 1 over c. Therefore, c equals 1, and y of x is equal to 1 minus x squared to the negative 1. And that is our solution. And it matches what we were given. And they want us to define where this exists. Well, we can't have the denominator equal to 0. So 1 minus x squared cannot be equal to 0. So x squared cannot be equal to minus x squared cannot be equal to 1. X squared cannot be equal to 1. X cannot be equal to plus or minus 1. So we got another problem. Verify that y of x equals to x plus c to the minus 1/2 for y prime plus y to the third equals 0. So in this case we have y prime equals minus y to the third. V then is equal to y to the minus 2. So v not yet. It's not coming yet.
Is it too black?
It's not here yet.
I mean, is it two black cords that go out?
What?
2 black plugs that go out, or 1?
No, we got that protector strip. It'll throw it.
Alright.
We don't have to do anything. It's
You can wash it?
yeah.
Alright. There is a plug in the
Don't
wall.
worry about it.
Alright.
So v equals 1 over y squared. So v to the minus 1/2 is equal to y. And minus 1/2 v to the minus 3/2 is equal, v prime is y prime. So now we have minus 1/2 v to the minus 3/2 v prime is equal to minus v to the minus 3/2. So what we want to do is we want to multiply through by v to the 3/2. So our multiplier is minus 2 times v to the 3/2. So we have v prime equals 2, and that's it. So that's dv dx equals 2, and that means v of x is equal to 2 dx plus c, and that's equal to c plus 2x. We can always pull the 2 out, and we have x plus c. That's v of x, and y of x is equal to 2x plus c to the minus 1/2. And so we have the solution. We can always call that c prime if we want to be a little more technical, and when we pull the 2 out we got a c. It's an arbitrary constant. So now the next part of the problem is, what do we have if y of 1 equals 2? So y of 1 equals 2. So we look at this, we have y of 1 equals 2 equals 2 times 1 plus c to the minus 1/2, and that's equal to square root of 2, 1 plus c, and if we square that, we've got 4 equals 1 over 2 times c plus 1. That's 8. And if we invert it, we have c plus 1 equals 1/8. So c equals 1/8 minus 8/8 equals minus 7/8. So we have then y of x is equal to 2 times x minus 7/8, and that's raised to the minus 1/2. So where is that defined? Well, we don't want this to be less than 0 or 0, because this is the same as 1 over the square root of 2 times x minus 7/8. So when the denominator is 0, y is undefined. So we want, and we can't be less than 0 because it's a square root. So we want x minus 7/8 greater than 0, or x greater than 7/8. So that's the region defined. Okay, so let's just check upon ourselves to make sure that we're right. That was problem number 3. So for 3, yes, x is greater than 7/8. Yep, we got everything exactly correct. All right, now let's look at one more problem. Why do I always do that? One more problem. And now, this one's cool. Let's look at this. This is y of x is equal to uh, 1 plus 2/3 ln of 1 plus x to the third and raised to the 1/2. And we want to verify that that's the solution to this equation. Y prime is equal to x squared on 1 plus x to the third, y to the minus 1, with y of 0 equals 1. So let's look at that. Now, we have a v equals y to the 1 minus n, so that's y squared. So v to the 1/2 equals y. 1/2 v to the minus 1/2 v prime equals y prime. And that's our substitution. So we have 1/2 v to the minus 1/2 v prime equals x squared over 1 minus 1 plus x to the third v to the minus 1/2. So we multiply through by 2v to the 1/2. And that gives us v prime equals x squared 1 plus x to the third. And that is it. Okay. So dv dx equals x squared on 1 plus x to the third. And v of x is equal to x squared 1 plus x to the third dx plus c. And we use a u substitution. So du equals 3x squared dx, and du on 3 equals x squared dx. And this, we forgot our 2. We multiplied by 2, and 2. So this is 2/3. 1 on u du plus c, and that's equal to 2/3 ln u. U is 1 plus x to the third plus c. And we take it back to v. So we take it back to y from v. So y of x is equal to 2/3 ln 1 plus x to the third plus c, all raised to the 1/2. But because y of 0 equals 1, we have 1 equals 2/3 times 0, because ln of 1 is 0, plus c to the 1/2. And that means c equals 1. So now we put that into the equation. We have 2/3 ln 1 plus x cubed plus 1 raised to the 1/2, and that is the solution. Now we want to know what interval that this is defined. We'll be all right. It's going to be okay. The storm's actually decreasing in power. You can see it.
We've got big
It's
lightnings.
going from red to green now. So, where is this defined? Well, we can't have
Hey, Graham. Hey, Dad. Hey,
1
Grandpa.
plus x to the 3 equals 0.
Grandpa,
What's that?
we just saw a lightning bolt flash that struck right on the mountain.
Great.
And then we saw a double flash right over our heads. We saw a double
Yeah.
flash.
A double flash. Did it strike in the same place?
No, it like struck over the house.
Not over our house.
Whoa! That was like the same thing, but it was like
Your
one
mama just texted that she will be here at 4:30.
Grandpa.
What?
Like one flash was right there, and it was like a dim stream of light to another flash over there.
Yeah.
And
It spread across the sky, huh?
yeah, and it got the blinding light again, and another blurry spot where it was, and another flash right where it was, like a double flash.
I see.
Really crazy.
So, in this situation, we can't have 1 plus x to the cube equal to 1, or 0. So x cubed cannot equal negative 1, which means that x cannot equal negative 1. And let's see how we are on that one. Yep. We cannot have x equal to -1. Yes?
What is the distance for counting of light?
Every second is 1,000 feet. 5 seconds is a mile.
That was a mile away. And it's on the back end of it.
Okay, let's look at this next one.
Just smart about it.
Yeah, just don't go by the windows or anything.
Come down here. It'll only be for a couple minutes.
Now,
You just
we're
have to be
given
smart about lightning, not afraid
this
of it.
problem.
Smart.
Verify that this is the solution to this problem.
Woo, that hit the leg.
C
It looked like it hit the leg.
squared minus, no it didn't, x third,
That was 5.
oops, 4 x squared to the 1/2, and y equals minus c squared minus 4x squared to the 1/2. And the function, the differential equation is y prime equals minus 4x times y to the -1. Yeah, there's the rain on the mountain. So, we use a v substitution, which is v equals y squared. V to the 1/2 equals y. 1/2 v to the minus 1/2. V prime equals y prime. And you substitute that back in. And we got 1/2 v to the minus 1/2 v prime equals minus 4x v to the minus 1/2. That means our multiplier is 2 v to the 1/2. And that isolates v prime equals minus 4x. And that's it. Okay, so now we have dv dx is equal to minus 4x. V of x is equal to minus 4x dx plus c. Thank you. And now we integrate. We've got c minus 2x squared oh, I made a mistake. That's what happens when you don't pay attention. Let's get that right. This is not 4x. We multiplied through by 2, so that's minus 8. Okay, so v of x is equal to 8 x dx plus c. And that gives us 4x x squared, but this is minus plus c, and that could be, c prime equals c squared, and so we have c squared minus 4x squared, and we have the relationship y equals v to the 1/2, so y of x is equal to c squared minus 4x squared to the 1/2, and that's our solution. We verified it. But it's plus or minus. Remember, y squared equals v. So y is equal to v to the 1/2 plus or minus. Okay, so we need both plus or minus, and that's our solution. Now, are there any other parts of this problem? No, that's it for this particular problem. So we're done with this segment, and we'll be doing a new section called separable equations.